Welcome back to my YouTube channel. Today we will discuss two important applications of intermediate value theorem. First application is standard version of intermediate value theorems and secondly is fixed point theorems. Okay. First of all, we discuss standard version of intermediate value theorems. Okay. That is, intermediate value theorem say that any function g on closed interval ab2 R is continuous and let lambda be any real number between g of a and g of b, then there exists a point c in open interval ab such that g of c is equal to lambda. Okay, that is, in graphically we mean that suppose this is my x-axis and this is y-axis. Okay, and x-axis represent the domain of the graph and y-axis represent the codomain of the graph or also range of the graph. Okay, suppose A here and B here. Okay, and my graph G, suppose this is my graph G of x. Okay, g of x, and the corresponding value here f of b, and this corresponding value of a here f of a. Okay, now actually the standard version is say that any lambda between this f of a and f of b, suppose here my lambda. Okay, any lambda between this, we can always find a corresponding c, that is my c1. Okay, between a and b, this a and b, open interval a and b, such that the value of c1 equal to lambda. Okay, and suppose any here we can choose any here, suppose there my lambda here. Okay, so the corresponding we can find a corresponding c here, suppose c2 here. Okay, corresponding c here, this is also between a and b. Okay, now the value of the f of c2 is equal to lambda. Okay, this is actually say we can find, this is actually say we taken any value between this f of a and f of b, we can always find corresponding a c such that this image of the c is equal to lambda. Okay, this idea of these theorems, this is idea of the theorems in graphically. Now proof in mathematically proof. Okay, now consider the function f of x equal to g of x minus lambda. Okay, here given gx is continuous, so f of x is also continuous. Okay, now lambda between g of a and g of b. Okay, suppose lambda between g of a and g of b. Here two cases are arise, either lambda g of a less than lambda less than g of b, or g of b less than lambda less than g of a. Two cases here, two cases are arise. Now case 1, suppose g of a less than lambda less than g of b. Okay, so now this is called it equation number 1. From 1, now f of a, value of f of a is equal to g of a minus lambda. From here, this is less than equal to 0 because lambda greater than g of a. Okay, now f of b, this is equal to g of b minus lambda. Okay, this value of g of b greater than lambda, so this is value greater than equal to 0. Okay, now applying intermediate value theorem. Okay, now by intermediate value theorem, there exists c belongs to a comma b such that f of c is equal to 0. Okay, now this implies, this is c. Okay, this implies g of c minus lambda is equal to 0. So this implies g of c is equal to lambda, and in this case hence the proof. Okay, and second case, if g of b less than lambda less than g of a. Okay, by similarly from 1. Okay, now from 1, value of g of f of a is equal to g of a minus lambda. So this is greater than equal to 0 because g of a greater than lambda. Okay, and f of b, this is equal to g of b minus lambda less than equal to 0 because g of b greater than lambda from here. Okay, so again by intermediate value theorem, there exists c belongs to open interval a comma b such that f of c is equal to 0. Okay, so this implies g of c is equal to lambda, and hence the proof. Okay, now second application, the fixed point theorems. Fixed point theorems say that if a continuous function f on closed interval to closed interval, okay, closed and bounded, this is closed interval ab to closed interval ab, then always find a c belongs to a and b such that f of c is equal to c. Okay, and this c point is called fixed point. Okay, now graphically we mean that here suppose here my x-axis and here y-axis. Okay, and graph of the function, suppose this is a graph of the function f of x. Suppose graph of the function this. Okay, this. Okay, and this is my point A, and this is my point B, and this is my point B, and this is my point A. Okay, this. Actually, fixed point theorem say that first we draw the graph. Okay, this is draw my graph. Okay, and draw the straight line y is equal to x. This is straight line y is equal to x. Okay, and next we need to see where the straight line y is equal to x intersect the graph and locate this point. Okay, this point, and this point. Actually, this point, suppose this point my c1 comma f of c1. Okay, and this point is c2 comma f of c2, and this point is c3 comma f of c3 and this point. Okay, and fixed point say that this point value, that is f of c1 is equal to c1. Okay, and f of c2 is equal to c2 and f of c3 is equal to c3. Okay, actually this means the straight line 2y is equal to x, where this straight line is intersect the graph, this point is a fixed. Okay, this is a graphical view of the fixed point theorems. Now mathematically we prove, also prove. So now mathematically we prove. Now proof, let's start the proof. We let hx function this equal to f of x minus x. Okay, given f is continuous and we know that x is also continuous and subtraction of two continuous function is continuous, so this implies hx is a continuous function. Okay, and also we see that the range codomain and range of f of x lies between a comma b. Okay, because here we define the function as follows. Here function domain of the function a comma b to a comma b, and also we know that function range of the function is subset of the codomain. Okay, so this is less than for all x belongs to a comma b. Okay, so this implies a less than equal to f of a. Okay, from here, and also f of b less than equal to b, this. Okay, no problem here. Okay, now h of a this equal to f of a minus a. Okay, from this inequality we can find this is greater than equal to 0 because value of f of a greater than equal to a. And now find f of b, h of b this equal to f of b minus b. Okay, from this inequality we can find this is less than equal to 0. Okay, now by the intermediate value theorem there exists a c belongs to open interval a comma b such that h of c is equal to 0. Okay, so this implies f of c minus c is equal to 0. So this implies f of c is equal to 0. Okay, and hence the proof.